So as yesterday we were talking about how to apply load on a frame, and just push over. You have to apply and then push. So there are several ways of doing that. So and as you Professor Datta yesterday discussed, one of the ways you apply the load according to its mode shape, and first is a fundamental mode. So how to calculate the fundamental? There are several ways of calculating. To begin with, say I can apply a load as a straight line. It's one of it. So that is a linear way. So according. So if you see that how it could be. So likewise you can do it. So this is a particular shape in which you can apply a load. So let's say this is a shear type of building. Shear type building means only deformation in the plane of this plate board. Okay. So that is one way only. So these are the degree of freedom. When we say shear building, these are the degree of freedom. So suppose any degree of freedom you can do it. So suppose these are the degree of freedom says, that means if we assemble a mass matrix, stiffness matrix, is a 3 by 3 matrix. So I have taken this example to understand what so far doing is in different way. The 3-story building, as you can see, and height of column, slab, everything is given. This is a plan of building. So this I took it as what last problem we did it. So there is a consistency between all the problems you taken for understand. And in addition to this, this response spectrum is given to you. Okay. The task before you is let's go down. Down. So you have to model this as a single degree of freedom system. Okay. So idealize the building as a single degree of freedom system for dynamic analysis. And now here it is mentioned, I stated mentioned. If not mentioned, as we did in earlier problem, half of the mass of the column you can lump at the top and bottom. That's what. So here I mentioned it specifically. Unit weight of this floor load and live load is mentioned. Concrete grade is given. Density of concrete is given. Masonry density is given because these are the masonry infills. Okay. So buildings, just like I shown yesterday, how to push our analysis. So after this problem, we will show how the push is done. So how you get the curve. So similar kind of buildings we do. 3 or 5 story?
5 story.
5 story. Okay. So now task before you when you have to design it. That's what we're talking about, the design part. So find the design value of bending moment and shear force, because ultimately we needed these two parameters: bending moment and shear force for design of any structure. If torsion coming, then it's a different way. But torsion we check it. Torsion cannot be a measure force for design. Okay, this can be. So you have to start with this. So how we go about this one? You have done that degree of multi-degree of freedom system? That is done? Okay, I have shown to you this multi-degree of freedom system. So how to start it? You need a mass matrix, okay? So here is matrix, here is matrix, here is matrix. Okay. So mass matrix, damping matrix, stiffness matrix. This is a forcing function. Okay. So you need a mass. Mass associated with these degree of freedoms. 1, 2, 3. So you can calculate mass. Okay. So this you can do it. I want to give a very simple way of doing this, very clear. So what you do is, first you calculate the weight of the slip, that is mass of the slip. So can you do it quickly? Start. So 1, 2, 3, 3 slips, है ना? So each one is same. So size is 6 by 6, and thickness is 200 mm. Density is given. So how much? Let me know. $18,000. That's all? Okay, good. So now floor finish and live load, it is already given. Floor finish is 2 and live load is 3. Okay? So how much it is?
18,000.
18,000? Walls. How many? 1, 2, 3, 4, 5, 6, 7, 8. Okay? Eight walls. And height of each wall. 3 meter. Thickness is 0.2 mm. How much here? This is height. This is thickness. Width.
3 meters.
3 meters is from center to center. So size of column is how much? 300?
300 mm.
So you have half of this. Because wall is this much only. Na?
2.7.
If you take center to center, the mass of this column and mass of this column is will come. Okay?
2.7.
2.7. So clear, all the emission is clear to you now? No confusion? Okay. So tell me. Two, 9, 2, 0. Good. Columns. There are 9 columns. Column is 3 by 3. Height is 3 meters. Density is known to you. Six zero. That's all. Now the column, there are 9 columns, okay? Now if you come here, if you look at this column, if you lump half of mass here, half of mass will come here, okay? But if you come to here, only half of mass will go to top. Here it get full, here it get full. Here is only half, okay? So this is why I did it here, all this separate, okay? So total mass is how much? You sum up all? 6?
6, 7,
Hmm?
995.
995. Okay. So that means your full mass is lumped. Okay? Each level full mass is lumped. Hmm? But if you at the top level you come, then how much mass is there? So this mass you have to reduce. Hmm. So this is mass M. The top mass I will call is alpha M. So you tell me how much it is.
64957.5.
64957.5.
957.5.
Okay. So to make this simple one, that is what I am doing. So now this total mass is known to you. What I said is this top mass is a some fraction of these two masses. Okay. This mass is known to this mass. This you can also calculate. Absolute term you can calculate this. But what I said this mass is in a fraction of this one, because only half of mass is going. Okay. So this will help me in the calculation, reduce the numbers basically. Okay. So can you, if I do like this one, what is alpha? Because top mass I am expressing in terms of a total mass.
0.95.
Point? 0.95. That's all?
0.955 to 0.9.
55. Okay, I can write it still, because if you're doing calculator by hand, you can do it. Okay? this is suppose alpha, then how much this one and this one? If I take this as a 1, yes? Yes, it will be half. Yes, that is true. That is true. So whether you have done it or not, you could have done it. All everything is half. Here is full, everything is full. Wall as well as column. But here only half of mass is going. So half of means this infill will also then alpha will change it. Huh? Yeah, that will. Point 0.76. Now it looks reasonable. Okay, so now if I say this is alpha, then these are 1, 1. Okay. So this is if I apply this one, okay, this is lateral force feature. How much the shear at this level is? Alpha? At this level, 1 plus alpha, 2 plus alpha. Perfect. Now there is a technique how to, now it's a refinement starts. How closely you can refine it. So what I do is, this is 2 point alpha, 2 plus alpha, I keep it this 2 plus alpha. This I add it here. So this becomes 3 plus 2 alpha. This 1 plus alpha I add it here. Okay. And if I add, this becomes 3 plus 3 alpha. Agreed? So because deflected shape will be always in proportional to the mass of the floor. Deflected shape is always proportional to the mass of the floor. Okay. So these are the masses basically, precisely rationalized mass. These are the rationalized masses. Okay. And then I have calculated the shear, which I easily can do it. Now I wanted to have, if I do this one, this is a unique shape. So this I added in metal like this one. Now what I do is, I divide all this, because rational I can do it. So I divide top, I wanted to make it as 1. So top I divide 3 plus 3 alpha, so it becomes 1. This is how much? Can you, so alpha is known to us? Huh? So this I divide. Okay. So now this is 3 plus 2 alpha. I divide by 3 plus 3. So our result is not altered. It remains same. If you can calculate, otherwise I can figure out something else. You do it better, I think. So how much it is? Alpha is 0.76, you can take it. Right? Very good. Yes. Now it is. 0.855, है ना?
Yes.
Okay. So I can write 886, okay? Okay, good.
0.522.
0.526. So I can write 53,
Yeah.
52,
522.
52, no?
522.
Okay, good. Now there is a still, so there are two ways of it. Either I can calculate this through the this characteristic equations. K is equal to eigenvalue problem. I can solve. You have already done the eigenvalue problem. You solved the eigenvalue problem or not yet? You done it, no? Okay. So instead of doing this thing, I'm doing this a different way. Okay? So I can skip all those mathematics, large size of mass and everything, because if you see what is the order of the mass is very large. So if mass matrix you assemble it, very large mass. Like similarly, stiffness matrix, size of matter, numbers will be very large. So in order to handle those things, I made a very simple things, either one or fraction number. So easily you can handle it. Okay? As long as I am using the linear deformations. Okay? So this is valid, this has a limitations. Okay? Now still I can rationalize this one, still I can do it. What I do is, again this, here I add this plus this, here I add this total plus this. Again I divide the top number and still. So I get more refined vector. So these are nothing but a refined vector of mode shape precisely. So you can go on converging till you get a very small difference, minimum difference, then you can stop it. So you get a result more close to the true results. That is what beauty of this thing is. So instead of doing so mathematics, I can, so this is very simple to handle it. So still I can do it 0.5, here 0.85 plus 0.52, this number plus 1, I can add it. Again top number, whatever I get it, I divide by the total number. So I get it 1, 1. So okay, let's do it. So you get difference, how much you get it. Okay? So do it once. That will be interesting, Anna. So this is 0.52. Here how much it is? 0.86 plus 0.52, how much it is?
1.38.
1.38. Okay. And add it 1 here, so 2.38. Okay. Now this divide by 2.38, so it becomes 1. This number becomes what? This one? 0.58. 0.58. Okay. This becomes what? 0.22. So that means the still difference is coming. Yeah? So still you can go iteration. So you can go until the difference between the two numbers is very small. You can stop it and say this is my fundamental mode shape. First mode is there. And first mode, why we are concerned in the building? Because almost say 80 to, it is more than 80, around say people say around say first 3 mode is around contribute 90% of the total mass. So that is why say first few mode is. Even solving larger problems, 7-8 modes for a building is good enough to solve. So that will give a fairly accurate estimate of the response. Okay, so this is a way of doing it. So I will stop it here itself. I will not use this vector. I want to show something else. So this is how the converging the result is there. Okay. Now my task is different. So you have to calculate the equivalent mass, equivalent stiffness, and this is the 3 degree of freedom. So how much mass participation is there? Okay. So my task is this. So having this known to you, the mode shape, how do you calculate these things? So this is if it's small by hand solution, this works well. So I give an equation to you. This is very simple way of handling it. So these are equations. This is a psi vector, that is deformations. Okay. So this you can do it very quickly. Huh? So if I do for you is that this mass participation. So M is 1. Second one is, I took it, this is alpha 1, just you calculate. Top one is 1. This is mass M1, this is 1 mass, alpha mass, okay? So this alpha 1, 1. This is 1, top is 1, okay? This one. This alpha 1 is 0.86, this alpha 2 is 0.52, okay? So you can get it this. Similarly, you can calculate the K. So you can calculate it. So this is, I said it's alpha 1, alpha 2, this is 1. Okay? So because the stiffness comes only when there are relative deformations. Okay? So this minus this will give the stiffness corresponding effective, and K is corresponding to that one. So each floor K is the same. K is there are 9 columns, 12 EI upon L cubes. E you know, 5000 under FCK. Column size is given, 300 by 300. I is known to, L is 3 meter is known to you. So at each floor the K is known. So that's why a K I had taken out. K1, K1, K1 or KI. And so it is same, so I have taken outside. So remaining is the relative. So this is why this is coming. And similarly, the mass term you can calculate is so how simple it is. You say the alpha 1, alpha 2 is a very small term. Had you taken the full mass, it's very large. And if that you square it, it becomes very large. If 5Z is number, if you square it. To handle it, it's difficult. So how to make it a simple one, that's what I did the exercise. So this you can calculate it. So this, how much K is coming? Can you, if you've done it, numbers you can tell me.
14056.
Which one? First one?
M is
M. M star?
no. L star is 2.38 times N.
2.38
times M.
L.
M.
M. Okay. Mass. Okay. Second one?
0.4056
0.4056
times K.
times K. Okay. So K is not to you. Right? K is not. And what about the mass? 2.01 M. Right? Now M you already calculated. So you know how much M is there. Okay. M is a total summation. All 6075, 2592, 18000, 18000. So all summation is the M here.
Would be 30.
So I you have calculated? Straight way equal because square column has taken. So concrete get FCK is 30. So you can use straight way here 30. So once you know it, so can you give me this number? This one? How much? This? Okay, just do it. Is how much? You're getting some odd number. Let's let other people see. Because K should be very large, na? Na? K is how much? This is your K, na? Each floor there are 9 columns. 12 is there. E is known to you. I is known to you. Only you have to be consistent with the dimensions. Here I took meters. This is mm square. So you have to be very clear.
73942.5 यही आ रहा है ना?
आते ही रहा है।
न्यूटन पर है।
आते ही रहा है। Point two per
K. Okay. So now your K is clear. So you can now tell me how much frequency is? Huh? Omega value. How much? 0.496 radian per second. Now I think you should not have confirmed. Everything I wrote to board for you.
23.26.
Omega, na? Now it seems. Yes, still I don't know how clear it is. 12 point? 12 point?
K star को तो ये भी लगा है क्या? 0.456.
14.79.
14.79.
ठीक है मैंने डायरेक्ट करी
15.7.
14.79. Who else? Anybody other answer?
15.
15.
15.7.
15.7. Okay, this is a difference. Difference should not be there. Now it's very simple. Had it you handling the number order is would have been not arrived at this point.
14.8
14.8
is right.
is right. Okay. So there's two answer match. So let's stop it here itself. Okay. So once you know this, now you can calculate the period. Can you calculate the period? Take it period, how much period is? Just take a reciprocal of this.
0.424.
0.424 seconds. Okay? Let's go, Dada. In. Now you come here. So now 0.424, you are somewhere here. In between 0.35 and 0.45. Okay? So now you go and have an interpolation at these 2 points. You are 0.424. Okay? So this is a linear variation. I made it like this. Okay? So this is 6, this oscillations, that is pseudo oscillations. So it's 6, and then you have it is 9. So in between you have double interpolations. Okay? So double interpolation you have to do it. First do it with abscissa, then with the ordinate. Actual responsive spectrum, you get it's a different kind of response. But here I made it this. Otherwise, if you go in the code, you'll find something like this. You should get around say 7, something like that.
7.5.
7.5. So your oscillation is, pseudo oscillation is 7.5 meters. Okay? Now, as Professor Datta is saying, there is a relationship exists between the oscillation and the displacement. So displacement, if you want to calculate, is So whatever yesterday I did, it will help us doing the things. And the maximum deformation you will going to get it is this. You mass participation, you calculate it is mass, normalized mass is there, and then pseudo displacement, or you call actual displacement. Displacement remains same either case. Sometimes people call by wrong pseudo, but it's a displacement only. How much? 104. 0.04.
0.0.
This is what is dimension?
40.7
Ah, yes, that is. Okay. Now, task before you is what? Yes, stop it. Now, task is find the design value of bending moment in the column of lowest story. Why a lowest story? Maximum. Yes. So, this displacement has come. So, how much bending moment would be? 6 EI. Anything else? Because this is the displaced vector. Your structure is 3-story. We have solved as equivalent single degree of freedom. That is what is written. Convert that is idealizer. So whatever we did is the idealization techniques precisely. So we converted 3 degree of freedom to the single degree of freedom. And reverse way we found the displacement at each level you can do it, or you can find out the bending moment at each level. So rather than solving a large size of problem, you can convert it to the equivalent smaller size of problems. That is what the trick is. So by hand solution, you take a larger problem and that. So hand solution give an insight to the problem. With help of computer, you can do n number of size. You can do it very quickly. But to get an understanding, if you do by hand, you get an insight in what exactly is happening. Okay. So rather than solving mass and steepness characteristic equation, finding the eigenvalue, then corresponding eigenvector, and then solving, combining, you can convert into the equivalent smaller size problem. That is what idealization I mentioned here. And you can do it very quickly, very fast. So 3 by 3 size, you can do it very fast. Okay? So how much this one, bending moment, you can do it?
kilonewton meter.
2.61.
261 kilonewton.
Okay, fairly good. 260 approximately. Yes, correct. Now you have a bending moment. Okay? Now that bending moment is in the lowest story. Now you can check with that moment the column size which you provided is sufficient or not. Okay? Now the bending moment would be same because if it is monolithic construction, the bending moment which is coming, the column would be same in the beam also. So now with this bending moment, you can check whether the size of column is sufficient or not. If you little extend this problem, it's interesting. Okay? Now first, before we break it, I can quickly take a 5-10 minutes. Okay. अब इसको हटा दीजिए, वो presentation है ना, वो खोलिए, last slide ले जाइए इसको. So now you got some interesting thing? Okay, good. So now in this I will share with one problem is left out. So you take this sheet and do it at home. When you tomorrow come for assessment, so you come with, okay, you bring all your stuff with you. Okay? You can bring book, notes, whatever studied, everything. Yes. So this is what Professor Arijit was talking earlier. The how to this one displacement calculation. Okay. So I will not go too much in the detail. I just want to throw some light so you are aware about what this is precisely and where it has an application. My point here is not to go too much about this one, but to show where is the application part is there. Otherwise, it's a very large, deep subject which you can go and study it. But my point here is just to show something, a glimpse of that, so you will appreciate it. So here is what it says: performance specific design. If foundation flexibility is taken into consideration, because foundation is there are two possibilities: either foundation rigid if it is in the rock, if it is in soil, it has a flexibility. Now, what effect it has on the structure response? That is the question here. Okay. So to begin with, so this is a statement. This I had taken from this book research paper of Presley. This performance-based seismic design. Okay. This paper is available. It's 12th World Conference 2000. Okay. So this paper is taken. And this book also, Presley book is also available. And most probably it's the 7th chapter, Howell and Presley. It's the 7th chapter, I think they deal with this ductility. So this statement, you can read it. The foundation flexibility increases the displacement at nominal strength V, and from delta Y is what? Yield displacement. Yield displacement. So I will make this diagram so you will understand better. The abscissa is displacement and ordinate is base shear. Now, as is standardized, this is a bilinear force deformation curve. So this is we normally take as yielding. So this is yield displacement. Okay. And this is a full flow of the deformations. So full flow deformation means a plastic deformation. Most of you call it is. That is what Professor Datta was talking about yesterday. So this is a delta P. Okay. That is a force deformation curve. Morning I have shown to you. There are two ways. One was idealized one, which is safe forming. Another one was a realistic, when you push a building slowly, how the deformation curve will come. So there is no damage, moderate damage, severe damage, collapse. The curve which I have shown to you. So it is later extension of that one only. So if rigid foundation, you can. So this is how when we go to the maximum level and corresponding, this is the displacement. So you get the maximum displacement here, and this is the yield displacement. Now this is valid when your foundation is rigid. Suppose foundation is flexible, what happens? The curve will have a less slope, and it goes like this one. So this blue line is for when foundation is flexible. Flexible means you have soil, this you have as a rock. Okay. So the slope will define what we use. So this yielding has, when you have a same structure is same. One case you have a flexible foundation, another case you have a rigid foundation. Because of flexibility of foundations, this has shifted slightly away from this. So this means this is your foundation effect. So I call it is a deformation in the foundation is delta. Okay? And the maximum deformation is this one. And the corresponding force in this one is shear is I call this with the same symbol I am using what is being given in this paper. Okay? So having said all those things, the displacement ductility. There are two ductilities. One is curvature ductility, another is displacement ductility. Curvature, M theta curve, the Professor Datta told you how the plastic hinge form. Another way is you have a displacement ductility. Okay. So displacement ductility, how you define this is a symbol. Porcelain and Prilly uses this one. This says delta y plus delta p. Delta y plus delta p, yield displacement plus plastic deformations combined with the total displacement divided by the yield displacement is the ductility. Precisely. So ductility can be expressed like this one. 1 plus delta p upon delta y. Suppose this is when the rigid formation is there. If you have a flexible foundations, then what will happen? As I shown on this one. I can write it. This is R rigid. This is a flexible. So if I read this one, this becomes delta P, and the denominator becomes delta Y plus delta F. This is shifting. So this total remains same. So now you can replace. If delta M is known to you, accordingly you can replace it. So you can reduce it. If your flexibility is 0, so delta F is 0, the same result you should get it. That's all. So this much is only extension I want you to show how the ductility is calculated. ductility is not precisely is the displacement. That is displacement is force deformation curve you plot it. The first yielding is delta y, that deformation is not in. The total deformation which you calculate is delta y. In between delta m and delta y, the deformation is your plastic flow plus size, that is delta p. And the ratio you thereby you calculate will give you how much the ductile structure is there. So how much the margin which is available, which allow the deformation in the structure. So when so she will doing it, even then he show the pusher curve, you will go how much the deformation is. So the curve will be interesting. The safe use. Any questions you have, you can ask me. Though I did very brief way, but just to give a insight to the things. That's all. Purpose. Otherwise, if you go at this, take a longer time. And thereby this ratio which I given plastic, you can read it. How the time will get influenced by. Any questions? No? So we'll